This is video 7 in our series Topics in Tensor Analysis. In the previous video, we had considered a generalized curvilinear system that had these curvilinear coordinate axes u1, u2, and u3. And again, we label them with superscripts. That's been the convention throughout the video series here. And then at a point P, we considered a tangent vector to u1, u2, and u3. And the way that we obtain those tangent vectors, the general formula is the partial of the position vector EI, the partial of the position vector with respect to UI. So to get E1, as you saw in the previous video, we take the partial of the position vector with respect to U1. To get E3, it'd be the partial of the position vector R with respect to U3. And then if we had some vector A, we could write it obviously as a sum of components on the u1 coordinate axis, its components on the u2 axis, its orthogonal projected components on the u3 axis. And since this is tangent to u1, then this could be the component of vector A on the u1 axis, where the tangent vector, now these tangent vectors here are not unit vectors. We could have made them into unit vectors as we commented on the previous videos. Typically that isn't done, so we're following that convention. So this is going to have a certain magnitude. So the component of vector A on u1 would be equal to some number times that tangent vector E1. And the component of vector A on U2 would be some number times this tangent vector E2, and same thing here. Now these components, we said let's write these with upper labels, with the superscripts. And if we do that, let's see where that leads us. So what we're going to do is consider this. Here we have two curvilinear systems, U and U prime, U1, U2, U3, U4, U prime 1, U prime 2, U prime 3, U prime 4. And for each one, we have the position vector R. We just didn't bother to draw it in. So here, for the U system, the position vector R would have components U1, U2, U3. That same physical quantity will have components in the U prime system, U prime 1, U prime 2, U prime 3. And as you've done in the previous videos, we're assuming that we know how to transform from U to U prime and from U prime to the U coordinate system. So with that in mind, we can say that the tangent vector to any one of these axes in the U system would just be as we did in the previous video. Indeed, that's a vector. Now, in the U prime system, that will equal the partial of R with respect to U prime I. So we could say that EJ that would be the partial of R with respect to uj. And now let's use the chain rule. We can write this in a slightly modified way. we could say, well, that would be the partial of u prime I with respect to uj, and then the partial of r with respect to u prime I. So when you use the chain rule, these just cancel out. We have the partial of r with respect to uj. However, if we look at this, we see that the partial of r with respect to u prime I, that is, and this should be e prime. What we'll do is when we write these vectors here, because we have the dashes here, we're not going to put the bars anymore. It just makes it too messy. But here, this then would be e I prime. Again, from here on out, we're going to leave the bar off. So we can say that this equals the partial of u prime I with respect to uj, this is a superscript here, times this. We can write it like that. So here then we have that ej equals the partial of u prime I with respect to uj times e I prime. And let's leave the bar off to be consistent now. And we know how to take these partial derivatives because we know the equations that take us from u to u prime and the equations that take us from u prime to u. So if you know those equations, then you can take these derivatives without any problem. So here then, this tells us that if we know a tangent vector in the prime system, then we know how to find its corresponding tangent vector in the unprimed system. And of course, if we want to, we could say, well, also ei prime that would equal the partial of uj with respect to u prime I times ej. So if we know the tangent vector in the unprimed system, that is the u-coordinate system, we'll call this unprimed and this primed now. If we know the tangent vector in the unprimed system, then we can find it in the prime system. Okay, now we had written, if we had a vector A, then that could be written as simply like this. This would be writing the vector A in our primed system. A1 times E1 plus A2 times E2 plus A3 times E3, just like we did over here, except now we're using primes because we're in the primed coordinate system. But that same entity, we can also write in the u-coordinate system or the unprimed system. So that would be a, let's say aj, ej. And again, when we have this repeated index where it appears uppercase and lowercase, it means you sum over that. So this would be A1 times E1 plus A2 times E2 plus A3 times E3, and so forth, depending upon how many coordinates you have in your system. But this is the same as that. Okay, now we look at this though, and let's see, we have AJ times EJ, but EJ, this is the same as that. So we can say that this then would be equal to A J, then we have this here, partial of U prime I with respect to Uj times E prime I. And again, this is the tangent vector for any particular coordinate here in our prime system. Okay, so here we have this equals this. So if we look at that, this and this cancel, and what we have is A prime I equals this, the partial of U prime I with respect to Uj times AJ. So this tells us if we have a vector in the U coordinate system, a vector A, in our unprimed U system, unprimed and primed, and if we know the components of the vector in the unprimed system, then if we take these types of derivatives, and notice we have a repeated index, that will then give us the coordinate of the corresponding coordinate in the prime system. And this, hopefully you recognize this by now, this is a contravariant transformation. If you remember from the earlier videos, and we'll write them out explicitly what we did before, but the point then is this, is that if we have a vector and we consider its components along each coordinate axis, and we designate those components with an uppercase letter, then when we transform from one coordinate system to another coordinate system, it behaves just like a contravariant transformation that we had looked at in the previous videos. So when we express the components of a vector when we express a vector in terms of its components along each coordinate axis and designate those components with an uppercase superscript, then when we go from one coordinate system to another coordinate system, the components of that vector transform along the pattern of a contravariant transformation. And we'll look at this and compare it to our previous results in the other videos in just a moment. What we also want to say, though, is that there's another way of expressing a vector. Now, here we have another set of curvilinear coordinates of U1, U2, U3, and so forth. And in the previous video we said, let's just consider two of them. This one in this one. We have a vector here, a vector A, and that will have a component on the U2 axis, which we designate like this. That's the tangent for it. And we multiply it by this number here, and it gives us that component there. And then the U5, that would have a tangent vector. Multiply it by the appropriate number, and that gives us the projection of this vector onto the U5 axis. So that would be the contravariant expression of that vector. However, for each one of these coordinate axes, instead of drawing a tangent vector like we did here, instead we could draw an orthogonal vector like we did here for the U2. This is orthogonal to the U2 coordinate axis. This is orthogonal to the U5 coordinate axis. Well, that same vector then we could express as having components on these orthogonal axes. We'll call them right now for lack of a better term. And that's another way that the vector could be expressed. So our vector can be expressed in terms of components along the axis, the normal way of doing business that we've always done before, or if we wanted to, we could also express this vector in terms of components along these orthogonal vectors that we make for each one of these axes. And it's another valid way of expressing the same vector in a different way. If you do it in this manner, what we're going to show in the next video is that when you transform from one curvilinear system to another, with the components here expressed on these orthogonal vectors, then it transforms not as a contravariant vector, but as a covariant vector. And that will show in the next video. Okay, now, do we recognize this as being a contravariant transformation? Let's just make some room and remember what we did in the previous videos. In the previous videos, we had considered again, just two curvilinear coordinate systems. Instead of calling it U and U prime, we call it X and Y, but it's the same deal with superscripts, and that we could transform back and forth. And what we showed in the very first video is that a displacement vector, its components, and this we established in video number 1, transform like this. If we knew the components of the displacement vector in the x-coordinate frame, then by taking these derivatives and summing over this repeated index, that would give us the components of the displacement vector in the y-coordinate system. And then we generalized, saying, well, a vector in general might transform like that. And this again is from the first couple of videos now. We're writing here. Like this, completely analogous to the displacement vector. We're now saying, instead of considering the components of a displacement vector, we're considering the components of a vector in general. We're saying if we're in one coordinate system and its components transform into another coordinate system by taking these types of partial derivatives, like we did for the displacement vector, and sum over that repeated index, that was a contravariant vector. And that is the same way that these transform. Here, we're having a vector that was in our unprimed system. Here, a component of it. Here's the corresponding component in the primed system. And to go from here to here, we take these types of partial derivatives, and we sum over the repeated index, just like we're doing right here. And here, this is a partial derivative of one coordinate system with respect to another coordinate system. This is the partial derivative of one coordinate system with respect to another coordinate system. So indeed, that is a contravariant transformation. So again, we want to emphasize here in this video is that we have a vector and we're expressing it as the sum of components along the curvilinear coordinates, but the components are written with superscripts. Then when we transform from one curvilinear system to another one, that then transforms as a contravariant vector. And in the next videos then, we'll consider in more details what happens with covariant vectors. So come back, join us for those videos, and we'll try and wrap up our discussion here with covariant and contravariant vectors, so we can later on, after that, we can consider what a metric tensor is. So come back and we'll continue our discussions.